structure. Here's a town of Decorah, and you've seen this already. It's kind of a dotted line drawn where the crater is. It's about 3.5 miles in diameter, so it's quite a bit smaller. That area, again, we've known there's been a lot of weird geology going on there for quite a while. And what we thought was that there was a major fault going through there. This was actually presented at the Iowa Academy of Science some time ago, showing why the units were so unusual up there. Well, if you look at the stratigraphy up there, this is a part of the strat column from a well nearby. We have a little Decorah Platteville formation on the top, some St. Peter sandstone, then the Perdocene group, including the Shakopee and the Oneota, then the Jordan formation down here in Lawrence. This is all real well-known geology. There's lots of drill holes into it. We know all about it. But a recent hole that was drilled up near Decorah came up with something like this. If we line these up on the top of the St. Peter, which is a nice mapping datum, we find the St. Peter is actually a little thicker there. But what the hell is all this stuff underneath here? It doesn't really fit into anything. Particularly this uppermost shale unit here. This is pretty strange. What we thought we might have here was a deeply incised valley. At the base of the St. Peter, before the St. Peter sands moved in, there was an ocean low stand worldwide. And so that meant rivers got cut down in deep channels as they worked their way to the ocean. And we know about some of these deep St. Peter channels around the state. We see them like that, and there's materials in them. Generally, that material is called the Reedstown, and it's kind of a soily residuum type material. Doesn't look anything like this stuff over here. So, you know, that idea was kind of bad. Plus, it didn't fit other parameters, but fortunately, we were doing some mapping up in that area, and there was one little exposure of weird shale that, in fact, turned out to be that shale unit, but it was only exposed right along a creek here, so we had to take some excessive measures to sample it, but we did, and that's kind of what it looked like, an unusual shale unit. Well, with that, we got a little money and drilled a couple short holes to figure out what we have. And there you see the contact between the St. Peter sandstone and this shale. We've since called that shale the Winneshiek Shale. And in mapping it, we find that shale, all the wells that encounter that shale are in green here, that circle of wells that include the shale fits right in a very circular pattern. So what is this? If there was a valley going through and that shale was related to that valley, we should have some other holes out here, not just constrained by a circle. So that was our first clue that we might be dealing with an impact structure there. And this is a geologic map that was produced from that. You can see that shale is exposed at the bed. Try this one more time. That shale is exposed at the bedrock surface here. This is where the upper Iowa River comes through. But it's covered with river alluvium everywhere except for that one little exposure up there. Otherwise, this shale unit sits underneath this purple unit, so it's buried by all these other rock units. Well, it turns out if we put a cross-section together based on these wells, we do have a nice crater-shaped feature with this Winneshiek Shale filling in the top. So that filled in the very top of the crater, and then a bunch of conglomerate and other debris filled in the lower part of it. Well, as an impact structure, that looks pretty good, except that it's way shallower than it should be. If you look at the physics on how impact structures work, it should be way down here or deeper. But it's another mystery that we're working on right now. We don't know why this isn't deeper than it is. So why do we know it's an impact structure? Well, in studying some drill cuttings that came from that, we find these sand grains, and these are kind of unusual sand grains. What it looks like is a quartzite. That's a rock that's made of a bunch of quartz grains that are glued together by quartz. But in fact, it isn't. If you cut a slab through here and make a thin section, what you see is something like this, a lot of fractures. These are called multiple fracture sets. They're not quite the PDFs that we looked at before, but they're very similar to it. We actually do have a few of those PDFs, the definitive evidence for impact. Here's another one of these quartz grain fractures there. But up in the corner there, you see that little area. If you'll zoom in on that, these are the classic multiple intersecting features that tell us this, in fact, was produced by a meteor impact. And we have enough of these that we know that it was related to this feature. We got a fellow named Bevan French working on this. He's a very, very famous impact scientist, and he's currently working with the Smithsonian, and he studied these little wider spaced impact features, and he did a study on some that we sent in from this crater. And this is kind of his spreadsheet, as he used what's called a universal stage on a microscope to measure the exact crystallographic angles of all of these fractures. And what he came up with was that these thin sections that he counted had fractures in them that were similar to planar deformation features from other impact sites that he's worked at. So that he considered that evidence that this was in fact an impact site. So, oh boy, we know this is an impact site. How cool is that? Well, if you look at the age of it, it was about 470 million years, something like that. There seem to be a lot of other Ordovician impact sites about the same age. And yellow dot there is a Decorah impact. This is a paleogeographic map, the way that the land looked like at the time that the St. Peter sandstone was being deposited. So at the time the crater was being filled in. There's a Decorah structure in yellow, and some other ones that are the same age in Sweden and the Baltic countries, and then in North America. Well, if we look, there seems to be an increase in impacts right there in the Ordovician compared to these other times. Or these more recent ones, we know of more of the recent ones because they haven't been eroded away so much yet. But we look at those older ones, this really sticks out. And so there was a peak in Ordovician cratering sometime between 150 or 450 and 480 million years ago. Well, it turns out that people that study meteorites, one of the things they do is they age date these meteorites. And there's a particular meteorite class of elchondrites that have what's called a breakup age of 470 plus or minus 6 million years. And what a breakup age means is this is when the metamorphic, or when the radiometric age of the meteorite was reset by a big energy and pressure event. So a couple of meteorites crashed together to reset these ages. So that's a common age. So that would probably go along with the age of all of these impacts. So the story that has been and is developing out of this is that if we went back 470 million years ago, up in the asteroid belt, we had a couple of these big asteroids that smashed together, and the pieces got knocked out of orbit, came zooming down to Earth, like yay, and created this series of impact structures, of which Decorah is one of them. So this makes for a pretty interesting story, but it gets even more interesting. Well, first of all, from the size of the crater, you can kind of estimate a few things. So we've estimated that the meteorite that caused the crater was somewhere about 1/4 mile in diameter. And one of these hits about once every 100,000 years. The crater that would have been blown would be about the size of the Empire, about as deep as the Empire State Building is high, about 450 meters or so. And we've got a whole raft of organizations that are working on this, and the Winnesheik Shale, that shale unit that's in there. Turns out that shale unit that filled the crater afterward is what we call a Lagerstätte. That's a sedimentary unit that exhibits extraordinary fossils of exceptional preservation. And Paul Liu is going to give a talk on fossils here shortly, and he's one of the lead workers that's working on this for us. It's really pretty interesting. I'm going to talk a little bit about some of this kind of stuff. I didn't coordinate with him. I hope I don't steal too much of his thunder. But in order to sample that shale, which you saw how hard it was to get at, we actually got permission to build a little coffer dam here and pump out the water next to the outcrop, and then go down and actually mine some of that shale for study. So this is what that shale looks like, very fine-grained gray shale, fine layering. And we collected about 5,000 pounds of this, and we put them in these little tubs because we have to keep them wet, because when they dry out, they kind of break apart, and we're keeping them wet for this study. And then we take them back to Iowa City, and Paul and his students split these apart and look for fossils. And you can find a lot of them. Here's an example of one of them. This is a carbonized film left from the imprint of a eurypterid. What eurypterids were like scorpions, like sea scorpions, or insects actually, arthropods that lived in the ocean. And what you have just left is that little carbonized film from those guys. And there's just an incredible amount of this carbonized eurypterid film in there. This is what a eurypterid looked like. Scale that up to something as big as me. Now it's interesting then, going back and looking at some of the history up here, what we found is that there were several newspaper reports of coal in this area. Well, you know, we're up in the Ordovician terrain, and you know, there weren't any land, hardly any land plants at that time, so we don't expect any Ordovician coal. So this was all pretty weird, we thought. Then we noticed that this one that talks about a certain amount of fixed carbon. Well, could that carbon be these Eurypterid carapaces that are preserved there? Or is somebody just trying to promote a coal mine that's not there? Well, kind of hard to tell, but it could very well be, because portions of this shale and those little carbon films, they burn easier than paper does. So that could be that there was just a little more contact of that, but we really found nothing that was comparable to that when we did our studies up there. So these are just a few of the fossils that are included in that. A wide variety of really spectacular things, and Paul will talk a little more about those, including these conodine animals. The recent news from up in that area, though, and I'm going to talk about this USGS survey in the next talk, was that we did some geophysical surveys up in that area, measuring various geophysical properties of the rock, and one of them was measuring the electromagnetics of the rock. With the airborne gravity that we did, this was the existing gravity map that we had. I'll talk about those a little later, if it's in the other talk. But the new gravity map that we have, if you blow it up, you can see a little hint of some sort of a dimple in the center of the structure. This is the line that we determined from studying the wells. So there's some sort of a depression there in the gravity data. So it tells you there's something of low gravity, of low density in there, like maybe broken up rocks from an impact structure. So that's pretty good. Now if we look at one of the newer pieces of information from this gravity survey, this is what's called the GZZ, or the vertical component of this gravity gradiometer. You can see it even more clearly. So we think we can actually see this crater in the gravity data. Then another thing that we flew was an electromagnetic instrument. That's what's being towed by that helicopter, that big ring. That outer ring is like a little cell tower sending energy into the ground, and it reflects back into this inner ring here, and that's the microphone that receives it. So with that, they can look at the resistivity of the rock and how resistive it is to electrical flow. Well, most of the rock around here is carbonate, is limestone and dolomite, and so its resistivity is fairly uniform, pinks with a little bit of reds and stuff like that. But the area inside our crater was bright blue. That bright blue is a very low resistivity region, and it's low resistivity because that's our shale. That's the Winneshiek Shale. And it's got a lot of carbon in it, it's got a lot of iron in it, so electricity moves through it a lot easier than it does the carbonates on the outside. So they basically have confirmed that, that the circle that these guys developed for the shape of the crater is pretty accurate. So we've seen Manson and Chicxulub. Unfortunately, this crater is a little too small to fit on this chart, so I kind of looked it up. And this would be about a 5.5 kilometer diameter crater. Would hit the Earth about once every 100,000 years, would land on dry land, one of the continents, about once every 200,000 years. So that's my little talk about our impact structures.